Uh, welcome. I welcome all to the 40 days CSIR Nadi Crash Course. Um, First 2 days, that is today and tomorrow. We will have the session from 7 p.m. to 8:30 p.m. And during this 40 days course, we will conduct weekend test, that is on Sunday. That will cover all the topics that completed during that week. Okay, and first 2 days, there is no limitation. Anybody can join. The participants, by kind request, you can share the link to your friends also. They can join to the class. And after each session, uh, we will give you a problem sheet with the answer key and sometimes the solution also. You can practice yourself during the daytime. You can also ask the doubt to the uh, faculty next day. If needed, we will arrange the doubt clearance session also. Okay, and today we have Dr. Hari Krishnan. He completed his PhD with the JRF from National Institute of Technology, Tiruchirappalli, and the postdoctoral research from ISER Trivandrum. And we have all the faculties that most of them have completed PhD with the research with the JRF, and all are having very good experience in the field of this kind of net gate, like some competitive examination, assistant professor, PSC examination. Everybody is having a lot of experience in this coaching field. Today's session is from 7 to 8:30 p.m. We will record the session. Each session we will record. Next day, we will send you the recorded video link through your email. So all of you must check your email regularly. And one more thing, the email address that you have given must be used to log in your YouTube. Otherwise, if the the addresses are different, then you cannot view the recorded video. And if any problems, then you can write to us. You can email to us, or you can send text in the WhatsApp group. These are some brief introduction. And today, Dr. Hari Krishnan will explain how to approach the crash course and how to prepare. Okay, please, Hari Krishnan, now you can start.
Yeah, thank you. Thank you, Dr. Rashid. So I'm starting on. Hi. Just as said, he said that I am a postdoctoral fellow in ISER Trivandrum under Shaijimon research group. So I'm directly coming into my points and all. Wait a minute. I will share my screen. Okay. Yeah. Now you can see, I believe. Okay. So we can have some emojis over here. So with respect to my questions or my concerns, something I will ask, you can put a something like thumbs up if you are well understood. And if you are not understood, you can have down thumbs up as well. And you can raise your hand and you can comment your comment on whatever you want to be, or you are not clear about that sessions or clear about the questions and problems I have discussed. So that will be a good. Oh, yeah, fine. So you can have so many emojis and you can test it on. Okay. So hi all and good evening. Very best evening, I believe. So I'm starting on. I'm talking about classical mechanics now. Classical mechanics. So before going to that, and I have to discuss with some of you about something about the examinations point of view. Okay. Okay, now you can see this is some of the sheets based on classical mechanics. So you have last year and all, maybe in 2022, 23, 24, I will add on in time. So in 2022, you can check on the 5 marks questions, 5 marks questions from the part C sessions and 3.5 marks.
Harikrishnan,
Yes.
sorry for interruption. I
Yeah.
think your screen is not visible. Okay, no, it's okay, fine. Yeah.
It's
No,
visible, right?
yeah, it's visible now. Yeah. I think there's some lag, slightly, 1 or 2 seconds, few second lag is there. Now it's fine. It's open. Open.
Wait a minute. Okay, we'll check my connection. Oh, any problem with the connection side? Okay, 1 minute.
I think it's okay now. No issue.
No, it's okay, right? Okay, fine. Okay. So if there is any of the connections or something is failed, you can comment or you can raise your hand. Okay. So that should be good. Okay. So here we have some. I'm only discussing about the classical mechanics over here. So there are 5 marks questions, 5 marks questions from this. In February 2022, you can expect some more 20 marks questions from 5 marks sessions and 40 marks questions. That is 4 into 3.5. That is 40 marks questions from 3.B sessions as well. 3.5 marks as well. Okay. So and similarly in GATE also there are many questions from the classical mechanics nowadays. So the classical mechanics is one of the core subjects for qualifying JRF. That is CSIR, JRF. CSIR, JRF. We are expecting to write marks around 110 to 130 marks. We should write 110 to 130 for JRF. And also very clear about 100 marks. Safe zone. Safe zone. Okay. Or if you are very clear and you are scoring about 88 marks and you are writing all the answers as it was right and you believe that it is exactly right, then 88 marks. Don't touch any other. Don't touch any other, and other questions you have doubt. Okay, so these are the things. So this will be giving you JRF, and this will be hopefully you will get net, and this will be net. But one condition, so you have to be all the answers you entered should be right answer. Okay, these are the criteria for scoring JRF and all. If you don't have the much confidence in or if you have scored only, you have attended 60 marks only, you can try for a luck. Like some of the questions is you have 2 options and all, you can go ahead. Why? There is no probability of getting 60 marks and all. There will not be, we won't qualify. There's no chance for qualifications. So you can test your luck by checking on like A or B or C or D, like that, so that you can at least get to some safe zones. Something like you can get some net or some JRF and all. Right. Okay. That's all the things. And majorly, I want to talk to you like mathematical physics. You have to study your plan with something like mathematical physics, classical mechanics, quantum mechanics, statistical mechanics, and electrodynamics. These are the core subjects. And this should be when you start from beginning, the end and also you should have this. And actually, if you are starting with mathematical physics, in that is a basic things we are learning. That should, in the last session of mathematical physics as well, you should need that things as well. Like in quantum mechanics, for example, in quantum mechanics, I'm writing, so you are seeing that board and all, right? Hello.
Yes. It's fine.
Is it visible? Okay.
Yeah, it's fine.
Fine.
Yes.
Okay. Okay. For example, like I'm talking about probability initially. I'm talking about probability. So for probability, I am starting in the first class means, and for the quantum mechanics, for the last class also probability is required. Whatever normalization constants, finding out the normalization constant, expectation of x, expectation of energy, expectation of p square, expectation of x square. All these things are from beginning to end you need. In quantum mechanics, one thing only varying, the potential. V of x, V of y, V of z. This based on this potential only, our MSc based systems or in the CSIR questions are setting up. So varying the potential itself for a Dirac delta potential, finite potential, infinite dimensional potential, harmonic oscillator potential. All these things are only potential. Based on the potential, the question is varying for the first half of the quantum mechanics. That is first quantum mechanics part 1. And in the second part, that will be like, say, for angular momentum, some more finding out coefficients and probability. These things only in the quantum mechanics. Okay, for MSc students, and you can solely dealing with potentials. And the varying the potentials, the wave functions varies and the energy varies. That is the only thing in the quantum mechanics. And the same things, probability, expectation of x, expectation of energy, expectation of p square, maybe in the angular momentum, expectation of L square, something like that coming. None other than these things and all. And some part in the last part are relativistic, WKB approximation, something approximation methods for solving, wave function finding. These all things. Only these things for quantum mechanics. In coming to classical mechanics, we are dealing with some kind of Newtonian mechanics. Then some of the part we will deal with the Lagrangian. Lagrangian is a core. Then Hamiltonian, phase diagrams. That is phase space diagram actually. Phase space diagram. Small oscillations. Then central force problems. Okay, these are the things in classical mechanics. But in classical mechanics, mostly we are dealing, most of the parts we deal with Lagrangian, Hamiltonian. That is in the for Lagrangian, Hamiltonian phase diagram, we require Lagrangian, and for small oscillations, we require Lagrangian, Hamiltonian, etc. But Hamiltonian mechanics, somewhat different sections, different things we need, force only we need. But all this, five four parts we required for topics is we required Lagrangian and Hamiltonian. So if you learn very well about the Lagrangian and Hamiltonian, then you can find out that is the basic thing. Like if you know the multiplications, you can multiply any number. And if you know addition, then you can add any number. Likewise, we can do if you know the Lagrangian or Hamiltonian and the phase diagrams, how to draw the phase diagrams from the basics and all, then you are clear about any of the problems as you are given, you can find out. So, and one of the thing I should say clear about, don't go for many books and all, but some of the textbook you have to refer for whatever I have, or the teachers you have taught you about whatever the things, and some of them, or many of in my lectures as well, some of the quantities like some may have negative. I accidentally I may put some energy like for a value like L is equal to Lagrangian 1 by 2 mx dot square minus v of x. Instead of minus v of x, that is potential, I will accidentally put plus. So it may lead you to some of the misleadings. So you should check on thoroughly on textbook as well when Lagrangian of the system is kinetic energy minus potential energy or not, or somewhat different or plus, something like that. You have to verify. That is one of the thing I have to say to you. Maybe it won't. I'm not saying I will make many more mistakes, but there may be a chance for everyone. So you have to at least check on one of the textbook depend on. I will suggest Ubadhyaya, JC Ubadhyaya, classical mechanism is JC Ubadhyaya and Goldstein. That will be very one who is starting, and Aruldas. These three books, textbooks, you can refer, and I have referred these three books for my problem solutions, finding out the problems, and the previous for solving and all. Okay, so you can go through this textbook as a reference, but understand how the Lagrangian is evolving and how you are dealing with. Then you can deal with any of the problems, and you clear idea about this systems, how it is evolving and all. You can solve any of the problems and you can crack it. So understand the problem and solve it. Okay, you will get a clear idea. So and one of the things, this is one of the thing I want to say. From the options, we can find out the answers using equation. Actually, it is like some we have many ways of solving. So you can use using units and dimensions. Some of the questions may concern about finding force. You know the unit of force. What is the unit of force?
Newton, sir.
Yeah, MA, and that is Newton. Okay, MA. So mass into acceleration, kilogram meter second raised to minus 2. Either. So using the dimension of the unit you are checking on force, so you can find out, or dimensional equations like, if I am writing the dimensional equation, don't misunderstood. ML t raised to minus 2 is the dimension of force. Okay, any of the following things containing dimension of ML raised to minus 2, that will be the answer. Maybe except maybe two options we show the dimension of ML raised to minus 2. Then we cannot check this method. So you have to solve on the actual method of solving and all the things. Okay. So approach the questions and all clearly. Okay. And I'm starting with coordinate systems. You are very familiar with the coordinate system, but I'm starting with coordinate system, and I'm starting with degree of freedom and all. Newtonian mechanics, we will discuss it on later classes. Like Newtonian mechanics means force is equal to MA equations. So we will discuss it on later. And now I'm moving to the core of the classical mechanics, that is Lagrangian systems. We need a degree of freedom first of all. So for the degree of freedom, first of all, we require some coordinate systems. Which coordinate systems we are referring? Okay. So I am first of all begin with Cartesian coordinate system. Cartesian coordinate system, X, Y, Z. Okay. So let a small point P, the question X, Y, Z. I can represent it with a vector R. Okay. So in Cartesian coordinate, vector R I can written as xi plus yj plus zk. I, J, K are unit vectors and they are unique. They are unique in their own directions and they are perpendicular to each other. Okay, so I have to find out the velocity. I just have to take dr by dt of this one. That will be x dot I cap plus y dot j cap plus z dot k cap. This is a mistake. So some kind of y dot instead of y dot I may say y dot, but in actual it may not come here. So very careful. You should also refer to the textbook. Okay, v is equal to the velocity is equal to x dot I plus y dot j plus z dot k. Okay, this is a Cartesian coordinate system, and we can in the Cartesian some of the problems we will use Cartesian coordinate system. Coming into that, generalized coordinate is there. I will talk it later. But when starting with Cartesian coordinate system is a first system. So velocity we can find out. Then kinetic energy, I can write it as 1 by 2 m v square. If I know the velocity, I can write kinetic energy 1 by 2 mv square. Maybe I will symbolize it as by the letter T, capital T. Okay, this is Cartesian coordinate system. I can represent a position of particle by xi plus yj plus zk. In cylindrical coordinate system, next one is cylindrical coordinate system. Okay, just a brief only I'm talking about. So in a cylindrical coordinate system, we require okay, x, y, z I will write. So this is x, y, and z. Okay, so and suppose this is the cylindrical coordinates. Okay, cylindrical coordinate systems. Okay, and maybe I can choose this as rho. That is the radius of the cylinder. I can choose as rho. This is maybe I will choose this as z axis because in z axis all time y x y z. Okay, this will be the thing. So in cylindrical coordinate system, rho phi z are the coordinates. Rho phi z are the coordinates, or sometimes they may use r theta z. Okay, r theta z are the coordinates. Okay, here rho is the radius of the cylinder. Radius of the cylinder. Okay, measured from, very important, measured from z axis. I am measuring it from z axis. The radius of the cylinder measuring from z axis. Maybe it will be r or rho. It can represent. Okay, theta or phi is the angle made by rho. Very important, rho from x axis. Angle made from x axis. So maybe I can write the projection of rho over here, and this will be the angle phi. This will be the projection of rho. This is projection of rho. This will be rho, and angle from x to the projection of rho is called phi. Angle made by rho from x axis is called phi, and z is z. Length measured. Z is, length measured along z axis, or from xy plane, from xy plane. Okay, clear. So in cylindrical coordinate system, you have to find out the kinetic energy. Suppose you have to find out the kinetic energy. How will you find out? If I know V, I can write kinetic energy is T equal to 1 by 2 mv square. I can find out. Okay, so similarly, T is equal to, I know, 1 by 2 into some particle have a mass m. Suppose m x dot square plus y dot square plus z dot square is the kinetic energy of particle in cylindrical coordinate system. sorry, in Cartesian coordinate system. Cartesian coordinate system. Cartesian coordinate system. Coordinate system. So I know the kinetic energy of the particle in Cartesian coordinate system 1/2 mx dot square, velocity in the x direction and velocity in the y direction square plus velocity in the z direction square. Okay, but I want to convert it into cylindrical coordinate system. What I have to do? Yeah, I have to do the relation between r theta or rho phi with x and y axis. Okay, I will write same also. I can write x is equal to r cos phi. X in terms of, or I can write rho cos phi, sorry, r cos theta, or I can write rho cos phi. Phi, x is a distance, okay, this is x is a distance, and angle is phi, okay, and angle is a phi. If I am drawing a plane over here, like this is sorry, this is y distance and this is x distance, or this is x distance. I can find out this is phi, and the adjacent side will give you cos, you know, adjacent side will give cos. Cos theta is equal to adjacent side by, I will write equal to adjacent side divided by hypotenuse. Here hypotenuse is rho, so I can write adjacent side as hypotenuse into cos phi, that is rho into cos phi as x. So x is equal to rho cos phi. Similarly, I can write y as r sin theta if I am taking theta as the angle, or if rho and phi system in rho sin phi. X is equal to rho cos phi, y is equal to rho sin phi. This is the only thing. And the kinetic energy in cylindrical coordinate system, I can write by substituting x dot and y dot. You can find out from here and substitute, then it will be in the kinetic energy of the system will be in the cylindrical coordinate system. Okay, is it clear? I will write on. So similar, like whichever the coordinate system we require for solving a particular kind of problem, how will you identify the problem, which coordinate system is required? Based on the symmetries. How? Based on the symmetries, we will identify the coordinate system. Based on the symmetries, we will identify the coordinate system. You know, the classical mechanics deal with macroscopic particle. I am not coming into the pure base of the systems, but we don't need that things and all you learned in the classes as well. So how to deal the problems from the basics, that I'm much concentrating on. That's why. So x is equal to rho cos phi, y is equal to rho sin phi. So how will I find out the kinetic energy? 1/2 mass will be same, x dot square plus y dot square plus z dot square. So here very important thing is x is equal to, I am writing r cos theta, and y is equal to r sin theta. R sin theta, I am choosing theta because phi and all radius I will come with r. Okay, so that way. Okay, so x dot is equal to, what will be the x dot? What will be the x dot here? X dot equal to r dot cos theta plus, here r and theta are variable. How I understood it, r and theta will be variable. Here phi or theta can be varied according to the position of the particle. Rho will be radius, fine, but when it moves on, maybe from this point to it moves to inside, then r will vary. So if r and theta is varying, or r and theta, with r and theta we can generate or we can find out the complete solution of this system. then I can write x dot equal to r dot cos theta plus r as constant. Then I can write minus sin theta theta dot. Okay, x dot is same. Then y dot I can find out. Y dot is equal to r dot into sin theta plus r into cos theta theta dot. This will be the differentiation. Most of the people are making mistake over here. Variable coordinates are r and theta. When in some problems, some bead moving in a cylindrical system or in a bowl, r and theta will vary. If r and theta is varying, r and theta or z is varying. If r and theta, z doesn't have a meaning over here because z dot is z dot itself. It has no connection with r and theta. So, but in x and y is connecting with r and theta. So, x dot means r dot cos theta, r minus sin theta, theta dot, y dot equal to r dot sin theta, r cos theta, theta dot. If I am solving this one, x dot square plus y dot square, I will get 1 by 2 m into, very important, r dot square plus r square theta dot square plus z dot square. This will be the kinetic energy in a cylindrical coordinate system. This will be the kinetic energy in a cylindrical coordinate system. Depends on whatever the variables, how the particle movement is. Sometimes r may be constant, that is r dot will be 0 then. R may be constant, r is equal to constant means r dot will be 0. And if theta may be constant, phi will be in a conical angle, alpha will be, or semi in a cone, alpha or theta will be constant, then theta dot will be 0. Somewhat some problem, identifying the problem, I will deal with the problem, then you will clear about this. Based on that, we can modify the kinetic energy. So it is clear about 1 by 2 m into r dot square plus r square theta dot square plus z dot square is the kinetic energy in the cylindrical coordinate system. I am coming to Lagrangian, that's why I am writing about kinetic energy first. That is very important part of the Lagrangian. Okay, clear? Any doubt? Yeah, if it is clear, you can put a thumbs up.
Yes, it's clear, sir.
Okay, fine. So this is the kinetic energy of the system. Okay. Then one more coordinate system is there. Spherical polar coordinate system. Similar like, I will just give a brief of spherical polar coordinate system. X, Y, Z, and let R be the point. R is a variable, and if we make a sphere with R as radius, okay, and its projection on XY plane will be, suppose XY plane will be like this one. Maybe I can choose another color. Okay, yeah, this one. R is a varying quantity, and from the x-axis I will make angle phi. Okay, and from z-axis theta, making, okay, this is the point. Okay, clear? So r is the radius of the sphere measured from the origin. Suppose O is the origin, r is the radius of the sphere. For a spherical coordinate system connecting with the Cartesian coordinate, radius of the sphere. Okay, then what is theta? Theta is the angle made by r from z-axis, very important, z-axis, and phi angle made from angle made by, sorry, angle made by projection. Projection means this is the projection. Okay, this is the projection. R is this one, and the projection is these things. This one will be R sine theta. If this is a theta angle, the projection of R, that is from the Z axis, what is the projection of R from the Z axis is R sine theta, and this length will be R sine theta, and phi is the angle made by projection, that is R sine theta from X axis, from X axis, from X axis. That is, I can write X is equal to, so this is X, so I require the projection to here as well. So I don't know about this distance. This is phi, and the radius is R sine theta. So this will be cos phi, that is cos phi equal to adjacent side divided by hypotenuse. Here adjacent side I have to find out. Adjacent side equal to cos phi into hypotenuse. Here hypotenuse is, what is the hypotenuse? That is R sine theta. So that is R sine theta cos phi give the value of X. R sine theta cos phi is the value of X. X is equal to, that's why R sine theta cos phi. Similarly, I can find out Y as Y is equal to R sine theta sine phi. R sine theta sine phi. So the connection in spherical polar coordinate system is X is equal to R sine theta cos phi, and Y is equal to R sine theta sine phi, and Z is equal to, what is Z? What is Z? What is Z?
R cos theta.
This is the distance, so R cos theta. Very good. R cos theta. R cos theta. So we can find out X dot, Y dot, and Z dot. I'm not doing. You can find out here. 3 variables are there. Maybe X I will write for R dot. I'm keeping all other things constant. R dot sine theta cos phi plus R. I'm differentiating with respect to theta, cos theta cos phi plus R sine theta and cos phi if I am differentiating minus sine phi phi dot. Sorry, here cos theta dot. I missed the theta dot. Okay. So R dot sine theta cos phi plus R cos theta dot cos phi plus R sine theta minus sine phi dot. Clear? So similar, like you can find out Y dot and Z dot, and the kinetic energy of the system is 1/2 m into, very important, R dot square plus R square theta dot square plus R square sine square theta phi dot square. This will be the kinetic energy of a spherical polar system if X, Y, Z directions are there and all. And one more thing, this R can be in spherical polar coordinate. R can be varied between 0 less than R less than or equal to infinity. That is a variation of R. Theta can vary between 0 less than theta less than or equal to pi, and 0 less than or equal to phi less than or equal to 2 pi. This is a variation. This is very important. Limit of integration is also very important. While you are solving problems in electrodynamics and all, you require this range. For a spherical coordinate system, the range is 0 to infinity. Maybe for a spherical coordinate systems like hydrogen atom, for a infinite some systems like they can be vary from R can be vary from minus infinity to infinity as well. Okay, for a spherical coordinate system, and for a cylindrical coordinate system, R will be vary from 0 less than R less than or equal to infinity, and phi vary from 0 less than or equal to phi less than or equal to 2 pi, and Z as well 0 less than or equal to R less than or equal to infinity. Is it clear? So these are the basics of some systems. So we are dealing with these things. So it will be clear, right? Is it okay?
Yes, sir. Yes, sir.
Okay. Thank you. So I am moving to some constraints and generalized coordinates. So we will discuss come to quantum mechanics now. You are just I just brief all the coordinate system and all. So I can come to constraints. What do you mean by constraint? So this is one of the question, very important question. Is geometrical restriction to the freedom of movement. Freedom of movement is called constraints. Example, I have a board. It can move in X, Y, and Z direction. Okay, if I have two boards and it is connected by a system L length, this is called constraint. So if this ball want to move in Y direction, this length constrained the motion of this length connecting with this ball. This one to move in X, this one to move in Y. Suppose this one to move in X and this one to move in Y direction. Not possible. Why? They are constrained by, or these two balls can move only in X directions because they are connected. That is, if I am moving this ball to X direction, automatically the second one will move in X directions. Okay. So this L will restrict the moment of freedom of movement of the ball by 1 degree. So we can call it as a constraint. Next example, simple pendulum. Simple pendulum. So we have okay. We have a L length string and bob is attached to the end, which is called a simple pendulum. So it can move like this. Okay, move like this, and L is a length. So this position I can represent it by X and Y, X and Y, and let this be the angle theta. So it can only move in X, Y directions because it is constrained. It cannot move in Z direction. It cannot move in Z direction. So what is the constraint over here? OP equal to some OP equal to L is the constraint. Length is the constraint for this system. Length is the constraint for this system. Clear?
Excuse me, sir. I have a doubt, sir.
Yes.
Sir, the bob cannot also move on along the y-axis, no, sir.
No,
Y-axis is
actually it will move in a plane, right?
yes, sir, yes, sir. XY plane.
Yeah, it will move in a plane. So if I have this one and the ball is moving over this plane, right?
Yes, sir, yes, sir.
So I need X and Y, but I did not require, or to the freedom of movement, I don't require Z axis. Clear?
Okay, sir.
XY
Okay, sir.
plane
Thank you,
only
sir.
required for the freedom of movement. So
Thank
that
you, sir.
okay. So that is the thing. So equation of motion I can write like I will come to degree of freedom and all. So it will be more clear to you. Just I'm saying the constraints first of all. So thereafter degree of freedom I will come. So I can write the equation of motion as x square minus 0, sorry, x minus 0 the whole square. So based on position coordinate system, simple only, y minus 0 the whole square is equal to L. That is nothing but equation of a circle. 0 in this coordinate system is 0, 0. X minus 0 the whole square plus y minus 0 the whole square. 2-point form. In mathematics, 2-point form it is. If I am connecting, this will be the length. So that is the thing I have written over here. This is the equation of motion of a simple pendulum. I can write. Okay. So then one of the thing is force of constraint. Yeah. What is force of constraint? Every constraint, I will write down every constraint followed. Constraints is followed by a force, which is called a force of constraint. In the case of simple pendulum, because of the mass of the bob, suppose it have mass m, there will be a force acting towards the downwards, that is mg. So this mg of force will exert a tension over the string in the string in opposite direction. This tension is called, you may be mistook with kinetic energy, not kinetic energy. This T is tension, dimension of force. Okay, tension. This tension is called force of constraint. Force of constraint. In other words, which is the constraint over there, it will exert some force to freedom of movement of the particle. That force is called, that force of constraint is called force of constraint. So in this case, tension is a force of constraints. Clear? Sometimes I am defining because it is very simple way I am defining you. If you find out any difficulties, you can ask me, or you are not clear, you can check it on me. Okay. So next is like classification. Classification of constraints. Classification of constraints. What is how they are classified? So there are two. One is holonomic, and second one is non-holonomic. Holonomic and non-holonomic. Holonomic means complete or entire or something like integral meaning. Okay, that is equilibrium or equal. Those constraints whose equation of constraint can be written as some form R1, R2, R3, etc., comma T in form of 0, equilibrium form or equal form, equality form. Then I can write this as, I can say this as holonomic. The constraint equation can be written in the form of an equation that is equal to a 0 or some kind of equations, which is called holonomic constraint. Okay. If the relationships that cannot be written like f of R1, R2, etc., comma T greater than or equal to 0, this is not equal. This is not equal. It is greater than or equal. It can be greater or it can be less than, or it can be greater than. I can write a greater than or equal or f of R1, R2, etc. T, less than or equal to 0. These are non-holonomic constraints. These are non-holonomic constraints. You may not be clear or not. You are clear? What is holonomic and non-holonomic?
Sir,
Doubt.
sir, there will that equal to will be there like f of R1, R2, comma T greater than or equal to is there in non-holonomic?
Greater than or equal 0. Greater than, maybe this greater than or equal means that I will explain. That is not exactly equal. That I can example. I will with example I will tell you. That will be better. Okay, holonomic example. Okay, clear. So I can write a particle. This is circle and a particle moving. A particle is moving. I will write a particle is moving. It is moving in xy plane in a circle of radius r. Circle of radius r. I can write z equal to 0 because this doesn't have a moment in I can write two equations, z equal to 0. Because this is in xy plane. This is in xy plane. You may know xy plane z equal to 0. In xy plane, there is no coordinate system for z. So z equal to 0 is one of the equations. And I can write one more equations like x square plus y square is equal to r square. These are the two equations. Two equations. So here, one of the constraint is there. Z equal to 0 is a constraint. This is a constraint. And the particle or some m mass particle is moving on the, not on, inside the circle of radius. Inside the circle of radius. Inside the circle of radius. And at every point, the particle has radius r. Every point, particle r has radius r. Then I can write x square plus y square is equal to r square. In case of simple pendulum, second example, in case of simple pendulum, I can write mod x, root x square plus y square is equal to L, because the length is inextensible. If L is inextensible, L equal to a constant. L equal to a constant. This is one of the equations. This is one of the equations. And next one is z equal to 0. So there are two constraints. There are two constraints. Two constraints. Two constraints. Suppose I'm coming to the point, then it will be clear to you later on what I'm talking about and all. This is one constraint. And here L equal to A, that is constant, and Z equal to 0. It cannot move in Z direction. So there are two equations I can write. And these are two constraints. Two constraints there. Here only one constraint. Clear? For a non-holonomic system. Non-holonomic. Non-holonomic. Non-holonomic system. Suppose consider a sphere. Consider a sphere. Consider a sphere of radius r, and a and an and moving on the surface of the sphere. Surface of the sphere. Surface of sphere under gravity. Under gravity. Suppose. Okay. This I can write by making x square plus y square plus z square greater than or equal to a. Greater than or equal to e. Because in a sphere, suppose it is in x, y, z, it is a 3-dimensional. The ant is moving, or some person having mass m is moving on the surface. On the surface, which means not exactly the radius is a or r. Or r. It should be greater than the particle position of the particle p. Suppose OP is greater than or equal to r. Greater the OP is greater than or equal to r. That is, position of that ant is greater than or equal to a. Then that kind, that is considered sphere of radius r, and ant moving on the surface of the sphere, moving on the surface of the sphere, not moving inside the, not moving inside the sphere, not moving in the radius of the sphere, but moving on the surface of the sphere and moving inside the surface of the sphere. This will be root of x square plus y square plus z square less than or equal to a, or what will be the radius r? I reckon of this one. R. These are non-holonomic, and if it is inside the radius of the sphere, inside the radius of the sphere, then there will be holonomic. It will be holonomic. Otherwise, it will be non-holonomic. Okay. Next one example. example 1 and example 2, I have a box. Okay. Movement of gas molecules inside the box. Inside the box is non-holonomic. So the particle can move inside like 0 less than x less than. Suppose A it is a cuboid. Cuboid means volume should be a cube. Okay. So 0 less than y less than or equal to a, 0 less than z less than or equal to a. So the position of the gas molecules with inside. So this can be written as a less than or equal to or greater than or equal to symbol. So that is non-holonomic constraint. Clear? Any doubt? Hello, is it clear?
Yes, sir. It's clear, sir.
So that will be good. Then next is scleronomic constraint. Scleronomic constraint. Scleronomic constraints. Have you heard about this? Time.
Time independent.
Yeah, time independent constraints are called scleronomic constraints, which means this type of constraints, constraints equation does not have any time explicitity. Does not have any time explicitity. For example, okay. So suppose a rod, okay, of length OP, and theta is the angle x, y. This theta is the angle. Then I can write this as tan theta equal y is equal to x tan theta. Okay, this is a equation type, or y minus x, or I can write y minus x tan theta equal to 0. This is an equation. Holonomic. So this is of equation type. So I can write this is not explicitly depend on time. So I can write this is scleronomic and holonomic constraint. Holonomic, scleronomic, and a holonomic constraint. If like a time dependent explicit is there, we will call it as what we call
Rheonomous.
yeah, rheonomic constraints. Okay, rheonomic constraints. Okay, so time explicitly, that is just opposite. This is time dependent. Time dependent and explicit dependence on explicit depends on time. Depends on time. That's the meaning. Okay, so I can say a previous example like if sorry x, y, and one rod is there. Okay, one rod is there, and it is hollow, and a bead is there, and this rod is rotating with an angular velocity of omega. Rod rotating with an angular velocity omega. Then if it depends on angular velocity omega, this will be x, this will be y, this will be theta. I can write same equation, tan theta equal to y by x or x tan theta equal to y, but y is equal to x tan theta, but theta is equal to omega t. Based on time t, the rotation will change. At a time t equal to 0, omega may be 0. At a time t equal to t, omega may be some value, omega dash or omega. Okay, so this will be a time dependent. Y is equal to x tan omega t. Y is equal to
Sir, excuse me, sir.
Yeah,
What if the rod rotates with uniform angular velocity, sir?
uniform.
If angular velocity is uniform constant velocity, then will that not be a Rionomous, sir?
Yeah, u means omega is equal to a constant.
Constant, sir.
Yeah, omega equal to a constant means theta is equal to what will be the theta? Omega into t, right?
Yes, sir.
Omega into t. So this time t can be, suppose if it is t should be some constant, omega equal to constant. So here also rotating with some angular velocity omega, but time is the factor which depends on theta. Then
Yes, sir.
theta equal to omega into t. If t is equal to 0, theta equal to 0. And if it is rotating with a constant angular velocity omega,
So even if omega is constant, theta varies with time. So it will be
Yeah.
anyway. It will be a Rionomic constant.
yes, polynomial
Thank
and
you, sir.
ergonomic constraints.
Thank you, sir. Thank you, sir.
Okay, so some of the examples I will write. Examples like suppose particle moving inside an expanding sphere. Particle moving inside an expanding sphere. Suppose. So let's R be the radius, R0 be the radius. Sometime after. Next example. Oh. Okay, the radius will become this is V into T. So total R equal to R0 plus Vt. So I can write, right? V into T means x is equal to V into T. You know, V is equal to x by T is the velocity equation. So I can write x is equal to V into T, some distance. So radius of the sphere is expanding. Initially it was R0, it is a constant. And if it is expanding, means with respect to velocity. With respect to velocity and time, it is expanding. Okay, at the time t, the radius become r is equal to r0 plus vt. Then we will call this as a, we can express this equation by x square plus y square plus z square, z square less than or equal to r0 plus vt. R0 is greater than, okay, x square plus y square. Initially it was there, r0 plus vt. So this is an inequality. So it is a non-holonomic and Rionomic constraints. Clear?
Yes, sir.
Okay. So so things like basics of classification constraints, equations, holonomic, non-holonomic, clearonomic, Rionomic, and non-holonomic Rionomic constraints. Okay, then now the very important thing, degree of freedom. What is degree of freedom? The number of independent coordinates required to describe the state of the system. State of the system is called degree of freedom. Okay, suppose we have n number of particles. Let n number of particles. Okay, moving in 3-dimension. 3-dimension means x, y, z. N number of particles moving in 3-dimension. What is the degree of freedom? What's the degree of freedom?
3n minus k, sir.
I didn't say about n particles. I didn't say about any constraints over here. How you say 3n minus k?
Sir.
Only n particles.
3n.
Yeah. So understand the problems and whatever the questions, that is very important. Okay. So this is x, y, z. N particles. N particles moving in 3-dimension. Moving in 3-dimension, what will be the degree of freedom? 3n will be the degree of freedom. Each can move x, y, z. Each can move x, y, z. So one particle have 3 degree of freedom. 3 degree of freedom. So n particles can have 3 degree of freedom. 3 degree of freedom. That's the thing. Okay. Then if this is in 3-dimension, if d dimension, what will be the degree of freedom? D dimension, degree of freedom. What will be the degree of freedom?
nd, sir.
Yeah, nd. nd will be the degree of freedom of in d dimension. Okay. Now we have some constraints. Now we have some constraints. Suppose it be k. Let it be k. Then degree of freedom is equal to in 3-dimension. In 3-dimension, I can write n number of particles there for n particle system. For n particle system, 3n minus k will be the degree of freedom. In d dimension, degree of freedom will be dn minus k will be the degree of freedom. Clear? So very important. If the constraints are there, then there will be degree of freedom will get reduced. Okay. So now I will come to the problem sessions. 1. A particle is moving only in x direction. Moving only in x direction. What is the degree of freedom? Moving only in x direction. Okay. Moving only in x direction. A particle is moving only in x direction. What will be the degree of freedom?
n, sir.
1.
1.
1.
Yes, 1. So how will be n? A particle means that is very important. The question is very important. N particle. I don't say not n particle. A particle means one particle. One particle moving in x direction. Okay. So x direction, it is moving in x direction. What will be the degree of freedom? Degree of freedom is 1. Then from how you will write degree of freedom from equation? 3 into 1 minus. What is the constraints over here? So I don't know the constraints. Okay. What will be the constraints over here?
2, sir. Y and z direction.
2. So that is 1. That I can say that y is equal to 0 and z equal to 0 is the equation. These two equations are constraints. These two equations are constraints. Oh man, sorry. These two equations are these two equations are why? From another. Oh, what's happening over here? Oh man. Oh, some problem occurred. Sorry. Ah. Sorry, some error. Error from the part of the system, I think. It's automatically connecting to that. Oh. Sorry. Okay. So constraints, these are constraints. So x equal to not equal to 0 and y equal to 0 and z equal to 0. These are two constraints. Two constraints. So k equal to 2. So degree of freedom is equal to, sorry, I'm writing. Degree of freedom is equal to 3 into 1 particle minus 2, that is equal to 1. Clear? Is it clear?
Yes, sir.
Okay, fine. So now I am coming to two particles. So next you will say two particles. Two particles constrained to move in xy plane, constrained to move in xy plane. Then what is the degree of freedom? What is the degree of freedom? Can you comment? Two particles constrained to move in xy plane. Then what is the degree of freedom? Comment your answer. So if it is clear, so what will be the answer? Any comments?
2, sir.
Two. Two particles constrained to move in xy plane. Okay. There are x, y, z in xy plane. Two particles constrained to move. So they cannot move in xy plane. They can move only in z. Or xy plane means two particles constrained to move in xy plane. Then what is the degree of freedom? So in xy plane, okay, then z direction only they can move. The particle can move. So two particles move in z direction. So degree of freedom is 2. Fine. Then now two particles one minute.
Sir, I have a doubt, sir.
Yeah.
Sir, in the case of simple pendulum, we are saying that the bob moves in the xy plane. And along the z, there is no movement in the z direction. So, similarly here we have two particles moving in the xy plane. But how the particle so you are drawing the perpendicular to the xy plane to be along z axis, sir? How it is?
No. I will come to this point. Wait a minute. So two particles constrained to move in xy plane. Xy plane means z axis equal to 0. constraint to move in xy plane. Constraint to move in xy plane means z axis equal to 0, one of the equation. For a first particle, z1 equal to 0. For the second particle, z2 equal to 0. There are two constraints. Two constraints. That's why I come into these questions again. Two constraints. So from degree of freedom, that is 3n minus k, 3 into 2 minus 2, that is 6 minus 2, 4. Degree of freedom is 4. Which means two particle constrained to move in xy plane. I have misunderstood the questions, that's why. XY plane means Z direction it cannot move. Z axis should be 0. Two particles constrained to move in XY plane, then what's the degree of freedom? So Z axis equal to 0 for them. There are two particles, Z1 equal to 0 and Z2 equal to 0. So the constraints are two equations. So 2 are the constraints. So 2 constraints, 3 into 2 minus 2, 4. Here, these are moving constrained to move in XY plane. A simple pen like constrained to move in XY plane. So that is Z equal to 0 is the one of the equation. One equation, and length L equal to a constant is the second equation. So this is only one ball movement. So 3 into 1 minus 2. What is the degree of freedom? 1. What is the degree of freedom? 1. And which is the coordinate required? Theta. This is called the generalized coordinates. This is called the generalized. Theta is the generalized coordinate. Only one coordinate system is required for the moment to represent the pendulum. Clear or not?
Thank you so much, sir.
Still have doubt?
No, sir. Thank you, sir.
Okay. So then again, two particles constrained to move in xy plane, and distance between them is fixed. Find degree of freedom. Comment your answer. Comment your answer.
So constraint will increase by 1, sir, from when comparing with the above previous problem.
So what is the degree of freedom?
So 3.
Yeah, 3 into 2 minus 3, that will be 3. How? Yeah, I will explain. So this is very important. That is, I am saying the basics. From the basics, I am teaching you. From the basics, whatever I am starting from the basics till end, this is required. Not only for classical mechanics, for equipartition energy in statistical mechanics.
Sir, I have a doubt, sir. As far as we are dealing with 3 coordinates system, in 3 dimensions, we use 3n minus k. So if dimensions decrease or increase, we will change the number 3.
Yeah,
in 3n minus k.
Yeah, that's why I am saying now. If it is d dimension, I have to change
Yes,
it with dn minus k. I will come to later on. Some more distinctions are there.
Okay, sir.
I will come to that point. For a d dimension, for a rigid body, a degree of freedom of a rigid body in d dimension will be reduced to one particular value. That I will come to point. For two particles, which is constrained to move in xy plane, that is z is equal to 0 for these two particles, A and B, and one L is the length connecting them. So here, what are the constraints? For first A particle, Z1 equal to 0. For second particle, Z2 equal to 0. And L is equal to a constant. So what are the constraints? Three constraints. So 3n minus k equal to 3 into 2 particle k is 3. So 6 minus 3, that is 3. Degree of freedom is 3. Clear? So
Yes,
this
sir.
is a way of finding the degree of freedom. Clear? So from the basics, I'm teaching you. Maybe I don't know. In someone in the previous also, you maybe learned these things and all. Okay. So now I'm moving to some different questions. Okay, two particles. Two particles. This will be M1 and M2 are attached in a string. First particle M1 constrained to move on a surface of table, and another particle M2 hanged vertically through a hole. And it can move only in vertical direction uh, and length of the string is L. Find degree of freedom. So two particles M1 and M2 are attached in a string. First particle M1 constrained to move on the surface of a table, and another particle M2 hanged vertically through a hole, and it can move only in vertical direction, and length of that string is fixed as L. Find degree of freedom. Comment your answer. What will be the degree of freedom? What will be the degree of freedom? This is the questions you can expect on CSIR level or from TFR or just something. So comment your answer.
Three, sir.
3.
Little bit too.
2. How?
Sir, mass
One
M1.
constraint is the particle M1 moves only on the surface of the table. Second constraint is the second particle moves only vertically. Third constraint is length remains constant, sir.
Okay. So for another person, some
Sir, Z is equal to 0 for M1. Then for M2, X and Y both will be 0 as it is moving only in the vertical direction.
Okay.
And another one, L is constant. So there will be 4 constants.
Yeah, fine, exactly, good. So M1 particle which can move on the surface of a table, so it can have restricted moment of Z1 equal to 0. Okay. So suppose this is M1 and vertically through a hole, it is under M2. This is the mass M2. It can move only up and down. That means x2 equal to 0 and y2 equal to 0 for this one. It have only z2 not equal to 0. Here x2 not equal to for this particle x1 not equal to 0 and y1 not equal to 0 for mass m1, and for mass m2 this one. So z1 equal to 0 is a type of constraint, x2 equal to 0 is a type of constraint, y2 equal to 0 is a type of constraint, and L equal to a constant is a type of constraint. So there are 4 constraints, and 3 into 2 minus 4, 6 minus 4, 2 constraints. Clear? So the degree of freedom will be 2. So the degree of freedom will be 2. Clear?
Yes, sir.
Okay, so that is the thing. So simple. Maybe I will one more questions I can do. Then I will stop here. So like some double pendulum or something I will give you. Maybe in some okay typical question. Okay, two masses M1 and M2 connected to a massless rigid rod with M1 is constrained to move in x direction and M2 is constrained to move in xy plane. Find the degree of freedom. Find degree of freedom. Two masses M1 and M2 connected to a massless rigid rod with M1 is constrained to move in x direction and M2 is constrained to move in xy plane. Find the degree of freedom. How will you find?
Two, sir.
Yes, 2. How? M1 have only x1 not equal to 0 and M2 have in xy plane, M2 is constrained to move in xy plane. So M2 have
Z equal to 0.
y1 equal to 0, here z1 equal to 0, and here z2 equal to 0, right? Sorry, z equal to 0. So not required. I'm for mass I'm writing 2 and all. Okay. So z2 equal to 0. So there are whatever the constraints and a massless rigid rod. So suppose it will be a L is equal to a constant. Then totally how many constraints? 4.
4 constraints.
3 into 2 minus 4, that is 2 again. So degree of freedom is 2. Okay, so you understood the degree of freedom. So I have some problems on Lagrangian as well, but maybe we will look into this next session. Okay. Okay, thank you. So these are the things. Is it good for you? Hello.
Excellent explanation, sir. Sir, kind request, sir. While following the class, I could not take the notes, sir. If I take the notes, means I could not get sync with the teaching, sir. So
Yeah, sure. I
uh,
will share the PDF file to you. No worries. So
okay,
whatever
sir.
I have written here, I will give you. Whatever
Okay,
this notes, I will give you. And I have also a kind request to you. You will make it on some notes, as it will be good for your future as well. Maybe
yes, sir.
if
Yes,
you are
yes,
getting the PDF and all, it may get
yes, sir.
lost sometimes.
Yes,
So
sir. Yes, sir.
better you are
From the
written.
PDF, I will write, sir.
Yeah.
Watching the video again means it will consume a lot of time.
Yeah, yes. Okay. Thank you.
Thank you so much,
Thank you
sir.
so much. Okay,
Thank you so much, sir.
Thank you for your response.
Okay, thank you. Thank you, Harry. It was a wonderful presentation. Dear participants, we will send you the recorded video link and also the PDF of the lecture notes. Okay, and we will send you the some questions for practicing also. That most probably you will receive tonight or tomorrow morning. Okay, thank you.
Thank you all.